All right, we're coming into the home stretch of the semester here. Yay, yeah. 2 more weeks, 4 more class periods. Today we are mostly focusing on chapter 10, comparing two means, going back to t-distributions, mostly. A little bit with proportions at the beginning still. And I didn't put this on Moodle, but on Thursday, well, I needed to title the week to include this. We're going to start chapter 11 a little bit about linear regression. And we'll get into the most depth about linear regression next Tuesday. And then next Thursday is the review for the final exam day. So it comes to an ending pretty quickly, but there's still, significant things to learn. And let's start by looking at proportions again and making sure we feel comfortable with this. So this is, again, going back to the same problem as before. Let's just review what we were thinking about here. 2 types of metal detectors are used in airports around the world. One is too sensitive compared to the other, or at least we think it is, based on anecdotal experience, say, but now we want to set up a statistical test. Continuous wave detector and pulse field wave detector. If you look down to part A here, P1 and P2 are the proportions. Those are population proportions. Those are parameters. The passengers that trigger the continuous wave and pulse wave detectors. We're wondering, is the continuous wave detector triggered by a higher proportion than the pulse wave? We think that might be the case. And so that's going to be P1 bigger than P2 as your alternative hypothesis. Let's go ahead and write that down. Alternative hypothesis is going to be that P1 is bigger than P2. The null technically would be then that P1 is less than or equal to P2, but as always, it's good enough just to consider the boundary value where they are equal. And remember, as always, we assume the null hypothesis is true. We give it the benefit of the doubt when we do the test. We need a test statistic. And with proportions, we go back to a z-statistic, essentially using the central limit theorem as our justification for this. Though, in reality, again, as our book states, the central limit theorem is not really a precise enough thing to call a theorem. So we're really only, in a sense, using it approximately. It's going to be a z-statistic. It's going to be P1 hat minus P2 hat, the natural estimator for P1 minus P2, which is a good thing to consider here because you could write these hypotheses in an equivalent way. You could write the null hypothesis that is that P1 minus P2 equals 0, and the alternative hypothesis that P1 minus P2 is greater than 0. So to look at the difference in the sample proportions is a natural thing to do because of that. Thinking about this form of the same hypotheses. P1 hat minus P2 hat would be a natural estimator for P1 minus P2. And if you're doing random sampling, yes, it would be an unbiased estimator as well. To make it a z, I need to standardize it. I need to subtract its null value, or to subtract its mean, and divide by its standard deviation. What's the mean? Well, it's 0. I'll go ahead and put a minus 0 here, but I really don't have to because when you subtract 0, nothing happens, right? So I wouldn't necessarily have to do that, but just for emphasis, I'm doing that. In theory, you could be testing something other than the null being 0. You could test this being 0.1 or 0.2 or 0.3 or something, and then put a 0.1 or 0.2 or 0.3 right there. That's hardly ever done, to my knowledge. This is almost always the test that we do. But in theory, we could. I'll go ahead and put the minus 0 there, but you don't have to. Times, again, the standard deviation of what? The standard deviation of this statistic, this estimator for P1 minus P2. what would that be? Here's the answer. Well, okay. It would be, let me write it this way up here. Sigma sub P1 hat minus P2 hat. Technically speaking, if we knew P1 and P2 exactly, it would be this. It would be the square root of P1 times 1 minus P1 over N1 plus P2 times 1 minus P2 over N2. Now that kind of feels like it's pulled out of thin air. What's the justification for this? I don't want to go into a full justification, but let me give you the basic idea. P1 and P1 hat and P2 hat can be thought of, even though we're calling them proportions, they can be thought of as means. That's at the beginning of chapter 9. There's a discussion about thinking of these as being means of point binomial distributions that take on values of 0 or 1. And because of that, that means the central limit theorem applies to them. And you can say, for example, that P1 hat is approximately normally distributed with a variance equal to P1 times 1 minus P1 over N1, because P1 times 1 minus P1 is the variance of X1 itself. Divide by the sample size, that's going to give you the variance of P1 hat. Similar kind of thing for P2 hat. Why do these get added? Because we're assuming, I haven't stated this today, but we're assuming that we're doing random sampling from two independent populations. I should say independent random sampling from two separate populations. Independence comes in again. I've got these two populations, I'm doing random sampling for both, and the random sampling for one population doesn't relate at all to the random sampling for the other. They're completely random, independent of each other. That assumption means you end up adding the variances. Remember back in chapter 3? You got two random variables that are being added or subtracted, in fact. You add their variances if they are independent random variables. And then we take a square root to get the standard deviation. I could put that down here, but if I do, it's not so useful because I don't know P1 and P2. I can replace P1 and P2 with a natural estimator for them. And if I assume in the null hypothesis that they're equal, the best estimator I can get for them is to take the values of P1 and hat and P2 hat and pool them together, create this thing called a pooled proportion, just denoted P hat. And I can effectively replace the P1 and the P2 in both spots with P hat. And if you do that and factor it out, this is what you get. Where P hat is the pooled proportion, and there's two equivalent formulas for it. One equivalent formula is to write it as N1 times P1 hat plus N2 times P2 hat divided by N1 plus N2. And another formula for that is to write it as X1 plus X2 divided by N1 plus N2. Those will give you the same thing, because P1 hat is X1 over N1 and P2 hat is X2 over N2. And if you cancel out the N1 and the N2, it'll simplify to that. So either formula is okay to use for this pooled proportion. Should give you the same answer either way. You are combining the two samples into one big sample effectively. And you're saying, if I'm giving the null hypothesis of equality the benefit of the doubt, then why not combine two samples to get a big sample to be my best estimate for the common value of P1 and P2? You might wonder, is this still justified in calling this a Z since we're using an estimator instead of the actual population parameter? Okay, well, with all these things, it's good enough when the sample size is large enough. And once again, We're not being precise about how large a sample size is necessary. That would be a real advanced kind of statistics class, like a graduate level. Anyway, that's what you would use in the context of this problem. P1 hat is much bigger than P2 hat. P1 hat is 113 out of 175. And P2 hat is only 4 out of 175, evidently. Sample sizes are the same in this case. That's not necessarily the case. Yeah, both samples are size of 175. So that's the intuition there is we definitely are going to have strong evidence. We're in all likelihood going to reject the null hypothesis. The p-value is going to be very small. P1 hat was 113 out of 175, and P2 hat was only 4 out of 175. This one's about 0.645714, and the other one's pretty small, 0.022857. For the purposes of using this z-stat, we've got to pool these. I'll just go ahead and do x1 plus x2 over n1 plus n2. It's going to give 117 over 350. Because the sample sizes are the same, 175, the pooled proportion, this is p hat, the pooled proportion is going to be halfway between these two numbers, right? It's going to be their average since the sample sizes are the same. 117 out of 350. You should be in the ballpark of 0.3 something, 0.33, yeah. 0.33, 4286. And that is halfway between these two numbers. Up to rounding. If the sample sizes are different, and again, they could have been different, then the pooled proportion is not necessarily would not be halfway between them if N1 and N2 are different. It would be closer to the one with the bigger sample size. Does that make sense? Intuitive sense? If N1 is bigger than N2, the pooled proportion will be closer to P1 hat than to P2 hat. You're giving more weight to the one with the bigger sample size. So now just plug all the numbers in. Our z statistic therefore in this problem, P1 hat minus P2 hat, 645,714 minus 0.022857 is 0.622857. The pooled proportion, again, is 117 out of 350. Looking up here, I've got to multiply that times 1 minus itself. I can do this here. And also times 1 over n1 plus 1 over n2. Once again, the sample sizes are the same. 1 over 175 plus 1 over 175 is going to be 2 over 175. I'll just do that with one step here. So the thing under the square root is going to be that. Take the square root, gives me this. And yes, this ratio is going to be very big. 0.622857 divided by, that is about 12.35. A very extreme z statistic, a very small p-value. We've definitely got very strong evidence against the null. You'd probably be fired if you failed to reject the null here, okay? So the p-value on the table is off the chart. You could be somewhat justified in saying the p-value is approximately 0. Of course, it technically is a tiny positive number. What does the calculator give? Well, this will be 1. This will be 1 minus the p-value. Okay, yeah, it rounds it to 1. Okay, let's see if this works. Okay, it's so close to zero, it's rounding to zero. The p-value is essentially zero. Yeah, it is a tiny positive number, technically speaking. I don't know, 10 to the negative 50 or something. So small, you can be pretty confident in saying there's no way this happened by chance if the null is true. And therefore, we think the null is false, and we reject it. Therefore, reject the null. We have strong evidence against it, very, very strong evidence. Seems there's no way that P1 equals P2. P1 is definitely bigger than P2 here. The continuous wave is definitely more sensitive than the pulse wave, maybe too sensitive, right? We don't want so many false alarms. Can I clarify anything? The p-value, technically speaking, okay, let's be more careful. The p-value is the probability of observing a test statistic as extreme or more extreme as what we actually observed under the assumption that the null is true. Here's the test statistic I got, assuming the null is true. What is the probability that z is greater than 12.35? It's approximately 0. Off the chart in the table, calculator even gave 0, even though technically it's a tiny positive number. It's a right-tailed test. That's why this is greater than. If it had been a two-tailed test, if this had been a not equal to, I'd want to double the one-tailed p-value, but this is still close, so close to 0 that the answer would still be super close to 0, and you'd still reject the null. By the way, as a matter of philosophy, some people always do two-tailed tests, even though they might have a theory that one thing is, say, bigger than the other. Why? Well, because they end up doubling the one-tailed p-value, which makes it harder to reject the null, which makes them less likely to make a type 1 error. That's why. So it's kind of playing it conservative to maybe always do a two-tailed test. On to chapter 10. We were just comparing two proportions. What about comparing two means? And again, this seems a little funny because, I mean, proportions, like I just mentioned 15 minutes ago, can be thought of as means. But we are going to use something different here in chapter 10. It's more traditional in the context of when you're thinking about means in the usual way to say, we're going to ultimately use a t-distribution again. So chapter 7, we were talking about using normal distributions, z. Then in chapter 8, we went on to t-distributions for both confidence intervals and hypothesis tests on a single mean when, remember, the population variance is unknown. Chapter 8, we went back to, or excuse me, chapter 9, we went back to z with proportions. And now in chapter 10, we're going back to t. Back and forth we go. We're comparing two means. A firm receives integrated circuits in lots of 100 from two different suppliers. These data are obtained on the number of defective items per lot. So you see the numbers there? Pretty simple problem here. It says estimate mu1 and mu2 and mu1 minus mu2 means of numbers of defective items in a lot of 100 from each supplier. This is described in terms of means, but we could think in terms of proportions on this problem. We could try to estimate P1, P2, and P1 minus P2. In those cases, you'd have to divide by 100. Here, we're just focused on the number of defective items, so we're saying we're focused on the mean. But you could think of it either way. Proportions always can be thought of as means, if you divide by 100 in this case. Well, I plugged these numbers into my calculator ahead of time. In the stat menu, list 1 and list 2. List 1 is a sample of size 12. List 2 is a sample of size 10. These sample sizes are different. That's okay. What's the natural thing to do to come up with estimates? Use the natural point estimators. X1 bar, say, and X2 bar. And if we're after the difference, X1 bar minus X2 bar. And just like with proportions, we can look at the difference because we're interested in comparing the means. So in the stat menu, go to calculate and one variable stats. Make sure your list is right. List one, calculate. The mean is 4.16 repeating. This chapter 10, number 1. You could write mu1 is approximately the observed value of x1 bar, which is 4.16 repeating, which you could also itself approximate to say 4.167 or something. Mu2 is approximated by the observed value of x2 bar. I need list 2. Don't do the 2 variable stats, by the way. Don't do that one. That's reserved for samples that are the same size. So still do the 1 variable stats, but now change the list name. X2 bar comes out nice and simple to be 2. And then mu1 minus mu2, the natural estimator is x1 bar minus x2 bar. As an estimator, I'd use capital letters. As observed values, I'd use lowercase. To get 2.167. That is some evidence, excuse me, some evidence that mu1 is bigger than mu2, right? That's some evidence that mu1 is bigger than mu2 because the difference is positive. Is it statistically significant evidence? That's not so clear. I could try to compute a confidence interval. That's not asked for in this problem. A confidence interval for mu1 minus mu2. And if that confidence interval, if for a high enough confidence, did not contain 0, in other words, if it only contained positive numbers, you might say that's some pretty strong evidence that mu1 is bigger than mu2. Should I go ahead and compute a confidence interval here? Sure, why not? Problem doesn't ask for it. But let's go ahead and compute a 100 times 1 minus alpha % confidence interval to estimate mu1 minus mu2. As an abstract formula for the point estimator, I'd want to use capital letters, x1 bar minus x2 bar. Right, because this is a theoretical kind of thing. Then when I observe values, then I call those lowercase x1 bar and x2 bar. Plus or minus some margin of error. Just like I said a few minutes ago, we go back to t here. T sub alpha over 2 instead of z times what? What have we seen before? Well, when estimating a single mean, we've used, well, when we know sigma, we wrote sigma over square root of n. If we didn't know sigma, we used s over square root of n, and that's when we switched to t, in fact, when we used s instead of sigma. For the proportions, I think we talked about this last Thursday, we had a square root of, well, something kind of like this, except with hats involved instead of parameters, p1 hat and p2 hat. We end up, we're focused on the difference of two means here. We end up doing something somewhat similar to this, adding. It's taking the square root of the sum of two variances. In this case, it would be the square root of S1 squared, the variance for sample 1, divided by N1, the sample size for sample 1, plus S2 squared divided by N2. But how many degrees of freedom should we use? Degrees of freedom equals question mark. And that's important, right? Because that determines what T we should use. And the answer ends up being, depending on what you know about the population variances and maybe what you don't know is a better way to phrase it. If you assume the population variances sigma 1 squared and sigma 2 squared are equal, then you end up pooling the variances, the sample variances, in a way similar to pooling the proportions that we were talking about 15 minutes ago. If they're different, then you end up doing something different. And the degrees of freedom is also different depending on which one of these you use. So I think I will not finish this. I'm just going to leave this hanging at the moment. We're going to come back to it. Okay? Leave this hanging at the moment. We'll come back to this. Write a note to yourself. Degrees of freedom is question mark, so we will come back to this. In this case, you also might wonder, how do you pool the variances? It's kind of a tricky thing, actually. It's trickier than with proportions. What should we do in the meantime before we come back to this? Well, how about another problem about finding distributions? Based on some theoretical results at the beginning of chapter 10. Let X1 be a sample. There should be a bar there. Sorry. There should be X1 bar is a sample mean, excuse me, based on a sample of size 49 drawn from a normal distribution with mean 10 and variance 25. Or did I mean sample mean? Maybe I meant the original variable here. No, I do mean sample mean. Okay. X2 bar, there should be a bar above the X2, is a sample mean based on a sample of size 81 drawn from a normal distribution with mean 13 and variance 4. What are the distributions of each of the random variables that you see there? X1 bar and X2 bar individually. Some sort of standardized versions of those things, their difference, and some sort of standardized version of the difference. Well, for X1 bar and X2 bar individually, use the cornerstone theorem, right? X1 bar is a sample mean drawn from a random variable X1, you could call it, though that gets a little confusing with random samples, that has a normal distribution, and therefore X1 bar has an exactly normal distribution as well, with the same mean, right? The mean of the mean is the mean. Remember that? The mean of X1 bar is the same as the mean of the population, 10 in this case. And variance equal to sigma squared over n, right? There's sigma squared, or sigma 1 squared, 25, over sample size is 49. So 25 over 49 is the variance. And that means the standard deviation is 5/7. And based on the cornerstone theorem, since we're sampling from an exactly normal distribution, you can say x1 bar is exactly normal. If we were not sampling from a normal distribution, you could still say x1 bar is approximately normal by the central limit theorem. But this squiggle symbol doesn't technically mean approximately, means in this context, it means is or has this distribution. So that would be the answer for the distribution of x1 bar, and the distribution of x2 bar is going to be similar, normally distributed, but now with a mean of 13 and a variance of 4 over 81. Right. Sample size for x2 is 81. Part B, what's the distribution of x1 bar minus 10 over 5/7? What did I say it looks like we're doing there? Normalizing, or I use the word standardizing. Take a normal variable, x1 bar in this case, subtract its mean, divide by its standard deviation. That's standardization. That's a z. That's going to be standard normal because 5/7 is the standard deviation of x1 bar, because its variance is 25/49. x1 bar minus 10 over 5/7 is standard normal, n01. Part C, same kind of thing for x2 bar. 2/9 is its standard deviation because its variance is 4/81. That's also standard normal. D, x1 bar minus x2 bar. You would think it would be normal, right? And you would think its mean would be the difference of the two means. 10 minus 13 is -3. What's justifying this? I mean, that's intuitive. Hopefully that's probably true, but what would justify it? We'd have to go back to chapter 7. And the book does talk about this in the reading. It's one of the exercises, actually, an important exercise, this one here. Distribution of a linear combination of independent normally distributed random variables. When you form a linear combination of them, including if you do x1 bar minus x2 bar, that's a linear combination of x1 bar and x2 bar. A0 would be 0, A1 would be 1, and A2 would be -1 in that case. You add their means multiplied by the coefficients, which are 0, 1, and -1 again. So in the end, that means you really subtract the means. And you add their variances with the coefficients squared. Coefficients are 0, 1, and -1. The 0 squared doesn't affect things, and that's not in the summation formula anyway. A0 is not in there. A1 is 1, A2 is -1. 1 squared and -1 squared are both +1. So that means you end up adding the variances. 25/49 plus 4/81. Whatever that turns out to be, if you got a common denominator, I won't bother doing that. If this were a homework problem, you should go ahead and get a common denominator of 49 times 81, and then go ahead and add the fractions to simplify. Notice in part E, we're taking x1 bar minus x2 bar minus its mean, which is -3, written as 10 minus 13, divided by its standard deviation, the square root of the sum of the fractions I just wrote down, 25/49 plus 4/81. So once again, this is standard normal, n01. So theory is being used here. Chapters 3 and 7, you might say mostly. That's going to be useful in inference now, confidence intervals and hypothesis testing. But now we're going to come back and start to address this question by first addressing this question. How do you know whether variances are equal or not? We have to do a new test. And in fact, we have to talk about a new kind of random variable. Not Z, not T. Is it some other letter? Yeah, it's called an F distribution, which I think is kind of unfortunate because, you know, F is always like a function in math. But now we're going to talk about F distributions. Let's talk about it in the context of a problem. The cost of repairing a fiber optic component may depend on the stage of production at which it fails. Cost of repairing, so we're focused on the cost. These data are obtained on the cost of repairing parts that fail when installed in a system. Let's see. Repairing parts that fail when installed, and on the cost of repairing parts that fail after it's installed. So effectively, as it's installed, system failure and field failure after it's installed. A little confusing there. The sample sizes do happen to be the same here, both 61, but they don't have to be. Okay, you can do what we're about to do without the same sample sizes. You got two different mean amounts that are fairly significantly different, you might say. But the variances, sample variances, are fairly close. We might be justified in saying the population variances. We might be justified in assuming the population variances are equal, for the purpose, perhaps, of making this easier in one way or another. And that's what we need to justify here. We need to say, can we reject the null hypothesis that sigma 1 squared equals sigma 2 squared? Yeah, look at the parts A and B now. It is thought that the variance in the cost of repairs made in the field is larger than the variance for the system, but these numbers seem to be switched around. I've got the 10 number 8. Did I type this correctly? Was I using a different edition of the book? Because these numbers don't match the book. I'm looking at page 360. I think I must have made up different numbers here just for the sake of having something different, maybe because I assigned number 8 itself. Probably say this is modified. Let me just say is smaller. So in my modification, I've modified it. Okay. But doesn't that sound funny? In my modification, I've modified it. So this is not exactly number 8 now. Set up the null and alternative hypothesis needed to gain statistical evidence to support the contention and use the data to test the null at the 10% level. I'm testing the variances. And based on the fact of what I'm thinking, that the field variance is smaller than the system variance, it looks like I should, the alternative hypothesis should be that sigma 1 squared is bigger than sigma 2 squared. Equivalently, sigma 2 squared is less than sigma 1 squared, right? You look at the sample variances, this one's bigger than this one. It's not just the fact that the samples variances, one is bigger than the other. It should be based on how you think about things. You should always set up your hypotheses before you do any sampling. If you do it after the fact, it's kind of like cheating. Though there are people out there who do it after the fact, and so you should be aware of that. The alternative hypothesis is going to be that sigma 1 squared is greater than sigma 2 squared, and the null is that they're equal. Equivalently, I could write these hypotheses in terms of differences of variances, just like we did with differences of proportions, and we'll do with differences of means, in fact. However, we don't do it that way. Instead, we divide one by the other. And the reason is so that we can use the F distribution which is based on a ratio of two variances, not a difference. Okay. The theoretical justification for all this is in the reading. It's based on various theorems. We do things in funny ways so that we can apply the theorems. Although remember, when you're applying the theorems in real life, you're really only sort of applying approximate versions of the theorems. The theorems themselves are true. They can be proved based on precise assumptions, precise hypotheses. You can get precise conclusions. But in real life, the precise assumptions are rarely ever met. So we are, in a sense, only approximately using theorems. Even though there is no such thing as an approximate theorem. No such thing. We're approximately using theorems. I'm hoping it's good enough. That's why it's always good when you're on the job to not be the only person doing the statistics. To have another person, so you can blame them if you get it wrong. No, don't be blaming other people. But it is still good to have somebody else that you can bounce ideas off of and feel confident that you're doing things right, or at least more confident. So the question is, what's the statistic? It's called an F statistic, the test stat. Capital F is the sample variance S1 squared divided by the other sample variance S2 squared. And if you're setting this up, you should set it up in such a way that if you want to do a right-tailed test, the one labeled with a 1, the subscript of 1, does have a sample variance bigger than the one labeled with the subscript of 2. Or at least that's the idea ahead of time, if that's your theory. And this is going to be bigger than 1 here because S1 squared is bigger than S2 squared. We've got 24.9 divided by 22.7. 24.9 divided by 22.7. It is bigger than 1, so that's some evidence against the null hypothesis. But as always, the question is it statistically significant evidence? And my intuition here is, yeah, that's bigger than 1, but it's not much bigger than 1. I'm thinking this is not going to be real strong evidence against the null. We're not going to reject the null. That's just a guess ahead of time. 24.9 divided by 22.7. It's about 1.097. What's the p-value? Okay, let's use technology. The p-value is going to be the probability of observing an F statistic this extreme or more extreme under the assumption that the null hypothesis is true. However, to compute this, I need more than just this number. I need, surprise, surprise, degrees of freedom. And here's something extra strange. I actually need two numbers that represent 2 degrees of freedom, one for the numerator and one for the denominator. The one for the numerator is n1 minus 1, first sample size minus 1. The one for the denominator is n2 minus 1. However, I did make the problem for so that n1 and n2 are the same. 61 in both cases. In the books, number 8, they're different actually. Degrees of freedom for the numerator is n1 minus 1. That's going to be 60. And the degrees of freedom for the denominator is going to be n2 minus 1. That's still 60. They're the same in this case, but they could have been different. Put those degrees of freedoms both as subscripts of the F. And again, they could have been different. But the first one is the degrees of freedom for the numerator, the second one for the denominator. Can we do this with technology? Yes. Notice it's a greater than sign. That's as extreme or more extreme. So I need to do 1 minus a CDF value. CDFs correspond to less than or equal to signs. In the distribution menu, you can find an F distribution, an F CDF right there. Lower is going to be 0. Upper is going to be 1.097 in this case. Both the numerator and denominator have 60 degrees of freedom. So what I say I was guessing was going to happen here. I was guessing that this is not going to be strong evidence against the null. I'm guessing the p-value is not going to be very small. So I'm guessing not 0.05, not 0.1 probably even. It's probably going to be bigger than 0.2 or maybe even 0.3, 0.36. Approximately 0.36. Do not reject the null. This is not strong evidence against it. It's not sufficiently small. So we don't have strong evidence against the null, which goes against our theory in the problem statement. But in terms of actually doing hypothesis tests about the mean, it's probably a good thing, at least before technology came along, because it made some calculations simpler. But now that we have the technology, calculators, spreadsheets, etc., actually doesn't make a real big difference either way. When testing the means. But we're still learning about testing the variances here anyway. Yeah, the data to test the null at the 10% level, we've done that. We have not rejected the null. We do not have strong evidence that these variances are different. Take a 1-minute stretch break. Could this p-value be computed without a calculator? Not this precisely, without technology. Is there a table for the F distribution? Yes, though it's a fairly limited table over many pages. Yikes. It's in the appendix, if we're testing at the alpha equals 0.1 level, what you would want to do using the table is you'd want to find the page where the CDF value is labeled to be 0.9. That'll correspond to alpha equals 0.1. And this table goes over many pages. 1, 2, 3, 4, 5 pages. There's also another table going over 5 pages that corresponds to a CDF value of 0.95, meaning alpha would be 0.05. Our alpha is 0.1, so we want the first set of pages. The gamma 1 is the degrees of freedom for the numerator, that goes across the top heading. The gamma 2 is the degrees of freedom for the denominator, that goes down the column. For our example, they're both 60. So I keep turning pages until I see a 60 across the top, which occurs on the last page, 60. And I also want to go down to the row with the 60. And this number then, 1.395, would be the boundary of the rejection region for a 10% level test. So your F statistic, your observed value, would have to be bigger than 1.395 in order to reject at the 10% level. Ours is not bigger than 1.395. Symbolically, you could write little f sub 0.10 is 1.395 when gamma 1 and gamma 2 are both 60. Let's confirm that with calculator. So if I go back once again to FCDF and put 1.395 here instead and paste it, I should get about 0.9, right? 1 minus 0.1. Yeah, very close to 0.9. But what we're really interested in is comparing means. So back to a problem about two means. And this involves pretty similar numbers as the last problem. What in the world was I thinking when I typed all this? Did I copy these correctly? I typed these PowerPoints like 15 years ago, and that's why I'm not remembering what I did. Problem number 14. Okay, these are the numbers given in the book for number 14. They were not for number 8. So 8 was a modified thing. I must have somehow mixed up the numbers when I was typing these. The other funny thing is, you know, I've been teaching this now for this like the 4th year in a row, and I'm not remembering the fact that these funny things happened like last year. Guess I just expunged it from my mind. We're ultimately interested in comparing two means here. To decide whether or not to purchase a new handheld laser scanner, tests are conducted on the scanner currently in use and the new scanner, and these data are obtained on the number of 7-inch barcodes that can be scanned per second, evidently on some assembly line or something. So it's going fast enough to scan these many per second. That's pretty fast, it seems. So do notice that the new one has a bigger mean than the old one. X1 bar is 40, X2 bar is 29. For the samples, both of size 61, both the same sample size in this case, though again, they don't have to be the same sample size. We've got some evidence that mu1 is bigger than mu2. The question again is it statistically significant evidence? The first part of the problem says to do the same test that we just did in the previous problem. Test the null hypothesis that S1 squared equals S2 squared, but now at the 0.2 level, to be sure that pooling is appropriate, to compute a pooled variance. Notice part B, S sub P squared. The P stands for pooled, not proportions. In part A, notice the alpha is different. It's 0.2 here instead of 0.1. However, because S1 squared and S2 squared are the same as the previous problem, and N1 and N2 are the same, the test statistic for this problem in part A would be the exact same thing we got here. The one-tailed p-value would still be 0.36. But wait a minute, are we doing a one-tailed test here or a two-tailed test? It doesn't seem to say, does it? Well, if they don't say, assume it's two-tailed. Take the conservative approach that many people always do. And so that means doubling the one-tailed p-value. Although you might question, is doubling valid here because is this F distribution, is its PDF symmetric? It's actually not, it's actually skewed. So you might wonder whether doubling the one-tailed p-value is good enough for a two-tailed test here. But it really doesn't matter much because the one-tailed p-value is bigger than 0.2. The two-tailed one, when you double this, is definitely going to be bigger than 0.2. 0.72, say. We're definitely not going to reject the null here, just like the previous problem. But that's actually a good thing, like I hinted at before, because that actually means pooling is appropriate. And at least before we had a lot of technology, that made things easier. Why did it make things easier? We'll learn about it more on Thursday. But let me just say, one way it made it easier is it allowed us to avoid having to use this formula here. The Smith-Satterthwaite degrees of freedom formula. Yikes. I'm stretching the truth here, but I'm going to say it anyway because it's kind of funny. I think I'd never been able to use this formula without making a mistake. Oh, okay, that's stretching the truth. I have at times been careful enough to not make a mistake. But there are many times where I've used this formula where I've made a mistake. Smith-Satterthwaite degrees of freedom formula. When pooling is not appropriate, you've got to use this formula for the degrees of freedom. Now, of course, when I say you've got to use this, I'm lying a bit as well because the calculator can do it for you. So it really doesn't matter too much these days. You know, back when I was your age in the 80s, we had calculators, but we didn't have graphing calculators. Graphing calculators were a big new thing in the 90s. And nobody had a calculator that I know of that could do advanced statistics. Could do simpler statistics, finding means and standard deviations. Nobody had a calculator that I knew of that could compute this right there. Or if there was one, maybe it cost $1,000 or something. So most of our calculators could just add, subtract, multiply, and divide, and maybe exponentiate if you were lucky. So yeah, even 30 years ago, people had to use this sometimes. But we're not there yet. We're going to use that, or sort of use it with technology on Thursday. So pooling is appropriate here. So what does that mean? How do you find the pooled variance, SP squared? Again, the P stands for pooled. It's a weighted average of S1 squared and S2 squared. But the weighted average formula is a weirder formula than the one for proportions. for the pooled proportion. It's a weird formula. It's n1 minus 1 times s1 squared plus n2 minus 1 times s2 squared, all divided by n1 plus n2 minus 2. A more natural kind of formula would have been to use n1 times s1 squared plus n2 times s2 squared divided by n1 plus n2. But no, we subtract 1 there and subtract 2 there. Do still notice, however, that this thing in the bottom is still the sum of these two things. The weighting is weirder. The book does mention why it's done in this way, though it doesn't go through the complete derivation. It's done so that this random variable is going to follow a chi-square distribution so that you can use that fact. Yeah, that's the pooled proportion there. And you can use this formula when pooling is appropriate. When you have not rejected the null hypothesis that sigma 1 squared equals sigma 2 squared. Right? When it seems valid that to assume that the variances from these two separate populations are equal, or at least approximately equal. Then by pooling the two variances, we get a better estimate for the common population variance. And once you've got this number, then you can use it either for confidence intervals or hypothesis tests. The next page is a formula for the confidence interval. And this comes back to the first page that we did in class today, comes back to comparing it to this. Formula right there. Notice it's the same point estimator. X1 bar minus X2 bar plus or minus T sub alpha over 2 times the square root. The square root I wrote there is this one. Looks different than the square root here. But they would be the same if I replace both S1 squared and S2 squared by SP squared. Because then I could factor out the SP squared and be multiplied by 1 over n1 plus 1 over n2. These two formulas are the same if S1 squared and S2 squared both get replaced by SP squared. When pooling is appropriate, use this one in the book and use degrees of freedom n1 plus n2 minus 2. So for our problem, n1 and n2 are both 61. So n1 plus n2 minus 2 would be 120. Use 120 degrees of freedom, which I'm forgetting. That might be off the chart in the T distribution chart. Does it even have 120 degree of freedom line? Yeah, not quite. The biggest degrees of freedom they have on there is 100. So what do people do? Well, of course, you could always use your calculator. Some people take a conservative approach and round the degrees of freedom down to the nearest number in the table if they're insistent upon using the table. So use 100 degrees of freedom instead of 120. Is that justified? It is if you want to play it conservative. By decreasing the degrees of freedom, it is actually playing it conservative. Increasing the sample size plays it conservative. Decreasing the degrees of freedom plays it conservative. What does that mean? It means you're going to get a bigger T value right here, and therefore a bigger margin of error. And that's playing it conservative. In terms of hypothesis testing, if you play conservative and use the smaller degrees of freedom, you're going to get a bigger P value and therefore make it harder to reject the null and therefore make it harder to make a type 1 error. Some people would say, well, I'm just going to go ahead and use infinity for the degrees of freedom. which effectively means you're using a standard normal distribution as Z. These numbers, like the 1.96, correspond to the Z. Of course, we've got technology, so we don't really have to do any of those things. We can go ahead and do this with that many degrees of freedom. And for example, if you wanted, therefore, like to do a 95% confidence interval, alpha is 0.05, and you want to use your calculator and still use this formula, you'd have to figure out t. That means you'd need to use inv t, right, to find the critical value. Alpha is 0.05, I type 0.95 in there with 120 degrees of freedom. This should be close to 1.96. Maybe a bit bigger, maybe 1.97. No, I'm wrong. Oh, that's okay. Yeah. That's for alpha equals 0.1. I forgot to divide alpha by 2. So let me do it again. If alpha is 0.05, then use 0.975 here. This should be a little bit bigger than 1.96. Yeah, 1.98. Okay, so then it's just a matter of using the formula for the confidence interval. If in the problem, well, it doesn't ask to do a confidence interval. If we, I guess they do. And they're asking for a 90% confidence interval. So alpha is 0.1, and alpha over 2 is 0.05, and you use the other one that we got. I won't take the time to do it. If our confidence interval for mu1 minus mu2, for example, contains only positive numbers, that would seem to be good evidence that mu1 is bigger than mu2, right? Because you're talking about a confidence interval for the difference. Have I done a hypothesis test by doing that? You have, technically speaking, done a hypothesis test if you assume it's a two-tailed test, a not equal to in the alternative. If in doing a 90%, I'm not going to take the time to do the calculation, but if in doing a 90% confidence interval for this difference, if we got an interval that only contained positive numbers, which it could, because x1 bar is bigger than x2 bar, right? x1 bar minus x2 bar is 11. If the margin of error is less than 11, then our confidence interval is only going to contain positive numbers. And if we wanted to say reject the null that mu1 equals mu2 in that context, you could say that is true as long as you're thinking about it as a two-tailed test at the 10% level of significance, 100 minus 90. If we were doing a 95% confidence interval, then we could reject it at the 5% level of significance. So you actually can use confidence intervals to do hypothesis testing as long as it's a two-tailed test and as long as you're looking to see whether the interval contains only positive numbers or both positive and negative numbers. If it contained both positive and negative numbers, then you would not reject the null. That would not be statistically significant evidence that the means are different. I guess that's kind of the way they're phrasing this problem. It seems like they're saying just go ahead and do a confidence interval. Because they're not saying set up null and alternative hypotheses for the mean here. They're not saying that, but D kind of does imply it. If your interval from part C contains all positive numbers, that would be evidence to say the answer to the part D is yes. It appears the new laser reads more barcodes per second than the old. Then the average means the old. If it did not contain just positive numbers, but also positive and negative numbers, it would not, you would say, no, it does not appear to necessarily read more barcodes per second. They didn't actually ask you to do a hypothesis test here, but you can. and you use a t-test statistic. The typo here, it's page 346. That 0 should not be there. It should really be a subscript of mu1 minus mu2. Mu1 minus mu2 sub 0, which is usually 0. If you're testing the null hypothesis that mu1 equals mu2, an equivalent null hypothesis, you go back to thinking about differences, is that mu1 minus mu2 is 0. But we could test that this is something other than 0, like 2 or something. And then that would be the value of mu1 minus mu2 sub 0. This 0 should not be here. It should be a subscript of that. However, it's almost always that this quantity is 0 in the numerator of the fraction, because we're almost always doing this hypothesis test for the null. Just like with proportions, when I mentioned an hour ago, where did I mention it? Right here. Subtract 0 there. I wrote it as a minus 0, but because subtracting 0 doesn't affect anything, I didn't have to write it. It's a similar kind of thing here. This thing is usually 0, but don't multiply by 0. That 0 should be up there. Notice the pooled proportion is in there. Notice the degrees of freedom is n1 plus n2 minus 2 when we're doing pooling, when pooling is appropriate. On Thursday, we'll talk about what to do when pooling is not appropriate, which to me just makes sense with technology to always just assume pooling is not appropriate and always just do the technique in section 10.4. Okay. Have a good day.